Okay. So when we talk about water as something on Earth. And it's kind of interesting to think about the fact that being on Earth is very specific, and water is very specific. And so it's kind of interesting to look at what do we mean when we talk about the size of a drop of water. So, is there anything unique about water on Earth? And so let's just take a look, and let's pretend that we're hanging a drop of water from a surface. And what's happening, this drop of water, we're just going to look at half of the drop, okay? And so here's our drop of water. And it's going to have a radius of r, okay? So let's do a force balance, because what's happening is this drop, as I put more and more water in, it stretches and finally it'll drop. And when will it drop? It'll drop when the force down exceeds the force up. The force up is given by sigma, the surface tension of water. The force down is due to the mass. So the force will equal the mass times the acceleration of gravity, which in this case, the mass will be 1/2 of that of a sphere. So a sphere, it'll be 1/2 of 4/3 pi r cubed times the density. So that's the mass of our little half sphere. And then the acceleration of gravity. Okay? Now, we have our force down. What's our force up? Our force up is going to be the surface tension times the distance over which that's working. So the circumference of that circle is 2 pi r times the surface tension. And that's going to be, this is the force down, and this will equal to the force up. Now, we're going to put a force balance, so we're going to put those both in, we're going to equate those and see what radius of water gives rise to a drop falling off of that surface. So then what do we have? We have 2 pi r sigma is equal to 1/2 of 4/3 pi r cubed times rho g. Okay, now what we can see is, we can cancel out that r, and that becomes r squared. We can multiply both sides by another 1/2. So we'll take 1/2 there, we'll put another times 2 there. That gets rid of that term. We'll divide both sides by pi. That gets rid of the pi. So we have a 4 here and a 4 there. Things are getting messy, but magic is about to happen. We get sigma equals, that's all gone, that's gone, 1/3 r squared rho g. Okay, and so let's solve for r. So we're going to first off multiply both sides by 3, and so we're going to put r over on this side, and that's going to be equal to the square root of, because it's r squared, 3 sigma, and then divided by rho g. So what we see is if the fluid is denser, the radius is smaller, and if the gravity was stronger, the radius would be smaller for the same liquid. Let's go ahead and throw some numbers in there. And so we're going to say that, what is sigma? Sigma, we've said in the past, is 72 dynes per centimeter. And that's not a particularly useful number. We want to put it into SI units. And so that's going to be equal to 0.072 newtons per meter. Okay? While the force of gravity is equal to 9.8 meters per second squared, the density of water is going to be equal to 1,000 kilograms per meter cubed. Okay. So what we want to do is change newtons into kilograms meters per second squared. And so that's going to be equal to 0.072 kilogram meters per second squared over meters, so the meters cancel out, so kilograms per second squared. Now, putting this all in, we get R equals square root of 3 times 0.772 kilograms per second squared divided by 9.8 meters per second squared times 1,000 kilograms per meter cubed. Well, this looks like a mess, but have no fear. What we can do is start canceling things out. And so what we see is, first off, the seconds cancel out, the kilograms cancel out. This meter takes that to meters squared. This is a meter squared in the denominator of the denominator. And so what do we get? We get R equals the square root of, here we have 3 times 0.07, so that's going to be about 0.026, 27, well, 26 is close enough, 0.27 perhaps, and then divided by about 10 to the 4th. And this will be in meters squared, okay? So what we end up with then is the square root of oh, I'm too low, excuse me very much. So what we end up with then is that R is equal to the square root of 2.6 times 10 to the minus 5th meters squared, okay? Which would be equal to 0.26 times 10 to the minus 6th, so that's going to be the square root of 10 to the minus 6th is 10 to the minus 3rd. Square root of 0.26 is going to be about 0.5. So it'll be 0.5 times 10 to the minus 3rd meters, which is equal to 5 millimeters. Okay. And so what we see is that a drop is about that size. And so what we get to is there's a fundamental size for a drop of water on Earth. And it has to do with the surface tension of that water, with the density of that water, and with the acceleration of Earth. And so that is a fundamental constant, and that's very much material to how water moves in Earth, how raindrops are, the size of raindrops, and other basic geometric factors about water on Earth.